The real zeros of a polynomial function. So a couple of theorems that we'll be using, the remainder theorem and the factor theorem. The remainder theorem says, let f be a polynomial function. If f of x is divided by x minus c, then the remainder is f of c. And the factor theorem says, let f of x be a polynomial function. Then x minus c is a factor of f of x if and only if f of c equals 0. So that IFF stands for if and only if. And it means that it's bidirectional. So if f of c equals 0, then x minus c is a factor of f of x as well. So first, we're going to use the remainder theorem to find the remainder when f of x is divided by x minus c. And then we'll use the factor theorem to determine whether x minus c is a factor of f of x. So our f of x equals 4x to the fourth minus 15x squared minus 4. And we are going to determine whether x minus 2 is a factor. First, by finding the remainder. So x minus 2 is in the form x minus c, so c is 2. So what we need to do is calculate f of 2. F of 2 equals 4 times 2 to the fourth minus 15 times 2 squared minus 4, which is 4 times 16 minus 15 times 4 minus 4, 64 minus 60 minus 4, or 0. So the remainder when f of x is divided by x minus 2 is 0. And because the remainder is 0, x minus 2 is a factor of f of x. The number of real zeros. A polynomial function cannot have more real zeros than its degree. So another law we're going to use is Descartes' law of signs. And it will probably make more sense when we actually look at it applied to a function. So it says, let f of x be a polynomial function in standard form. The number of positive real zeros either equals the number of sign changes in the non-zero coefficients of f of x, or that number less an even integer. And the number of negative real zeros either equals the number of sign changes in the non-zero coefficients of f of negative x, or that number less an even integer. Okay, so our instructions here are to tell the maximum number of real zeros that each polynomial function may have. Then use Descartes' law of signs to determine how many positive and how many negative real zeros this function will have. And our function is f of x equals 3x cubed minus 2x squared plus x plus 2. The degree is 3, so the maximum number of real zeros is 3. Now we need to count sign changes. So for the positive real zeros, we have positive 3 to negative 2x squared, so that's a sign change. We have negative 2 as our coefficient to positive 1, that's a second sign change. And then from positive 1x to positive 2, we don't have a sign change. So we may have 2 positive real zeros, and if I subtract 2 from that, because 2 is an even integer, 2 minus 2 is 0. So I could have either 2 positive real zeros or 0 positive real zeros. To find the number of possible negative real zeros, we need to find f of negative x. So I will substitute negative x in for x. 3 times negative x cubed minus 2 times negative x squared plus negative x plus 2. Simplifying, we get negative 3x cubed minus 2x squared minus x plus 2. Now we need to count sign changes. So negative 3 to negative 2, that's not a change. Negative 2 to negative 1, that's not a change. But negative 1 to positive 2 is a sign change. So for negative real zeros, we can have 1. We would not subtract an even integer because 1 minus 2 would be negative 1, and we cannot have a negative number of real zeros. Okay, we also need to know about the rational root theorem. Let f of x equal a sub n times x to the n plus a sub n minus 1 times x to the n minus 1, and so on, down to a sub 1 times x plus a sub 0. Let that be a polynomial with integer coefficients. Rational roots will have the form p over q, where p is an integer factor of the constant a sub 0, and q is an integer factor of a sub n, which is the leading coefficient. So we're going to look at that for our polynomial f of x equals 3x to the 5th minus x squared plus 2x plus 18. So here our constant is 18. So that is our a sub 0. And 3 is our leading coefficient. That is our a sub n. Our p's will be factors of our constant of 18. So factors of 18 are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 9, and plus or minus 18. And our q's will be factors of our leading coefficient, in this case 3. So our q's are plus or minus 1 and plus or minus 3. So on the next slide, we're going to look at all the different ways of forming p over q. So for possible rational roots, I can take all of my possible p's and put them over my first possible q's. So everything I'm first putting over 1, then I can put them all over negative 1, then I can take them all and put them over 3, and I can take them all and put them over negative 3. So all of these will give us the possible rational roots, but we don't need to consider multiple occurrences. So let's simplify. That first row simplifies to these numbers, which are basically our p's. Our second row simplifies to these, which just differ in terms of which ones are positive and which ones are negative. And our third and fourth rows will simplify to plus or minus 1/3, plus or minus 2/3, plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. So now we need to figure out which ones are different. So we've got plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 9, plus or minus 18, plus or minus 1/3, plus or minus 2/3. And then we repeat ones we've already identified. So our possible rational roots are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 9, plus or minus 18, plus or minus 1/3, and plus or minus 2/3. We don't know which of these are rational roots, but these are the only possible rational roots we could have for that polynomial function. It gives us a starting point. So now we'll actually look at actually finding the real zeros of a polynomial function. And we'll go through a series of steps. We will use the degree of the polynomial to determine the maximum number of real zeros. We'll use Descartes' law of signs to determine the possible number of positive zeros and negative zeros. If the polynomial has integer coefficients, we'll use the rational root theorem to identify those rational numbers that could potentially be zeros. Then we'll use synthetic division to test each potential rational root. Each time a root, and therefore a factor, is found, we'll repeat from step 3 on the depressed equation or factor. So this is our first polynomial function. Y equals x to the 4th minus x cubed minus 6x squared plus 4x plus 8. The degree is 4, so the maximum number of real roots is 4. So using Descartes' law of signs, we have a sign change. So for 1, here's our second sign change, and that's it for positive real roots. So for positive real roots, we might have 2, or 2 minus 2 is 0. So we either have 2 positive real roots or 0 positive real roots. To find the number of negative real roots, we need to find f of negative x. So substituting negative x in for x and simplifying, we get x to the 4th plus x cubed minus 6x squared minus 4x plus 8. Here's a sign change, and we have a second sign change. So for negative real roots, we either have 2 or 0 again. So our p's are factors of our constant, which is 8. So those are plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. Our q's will be factors of our leading coefficient, which is 1. And these are the simplest ones because those factors, our q's, are only plus or minus 1. So then if we are finding the possible rational roots and taking all of our p's and putting them over all of our q's, because q is just plus or minus 1, the possible rational roots are going to look like all of our p's. Plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. Okay, so we have 8 possible rational roots. We know that since we are going to have a maximum number of real roots of 4, we're going to have either 2 or 0 positive and 2 or 0 negative. Remember, it doesn't have to be 2 and 2 because we're just looking at real roots right now. We could have some complex roots. Okay, so I'm going to set up for synthetic division. So again, if we go back and look at our polynomial on that last slide, we're looking at our coefficients of x to the 4th minus x cubed minus 6x squared plus 4x plus 8. So we're looking at 1, negative 6, 4, and 8. And we're not missing any terms, otherwise we would need to put in zeros as placeholders in synthetic division. So that's where those numbers came from. Now, going back one more time, we need to choose one of our possible rational roots, plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, to try for synthetic division, because we don't know which one, if any, it could be. So in real life, when you don't know what the answers are, this could take a while. So I'm going to try 2. For synthetic division, we will bring down that first term. We will multiply 2 times 1 and get 2. We'll add going down, so negative 1 plus 2 is 1. We will multiply 2 times 1 and get 2. We will add going down and get negative 6 plus 2 is negative 4. Multiply 2 times negative 4 and get negative 8. Add 4 plus negative 8 and get negative 4. Multiply 2 times negative 4 and get negative 8. And finally, when we add, we get 0, which is our remainder. So that means if we get a remainder of 0, 2 is a root. So now, we know x minus 2 is a factor. If I can go through this process again with 1, 1, negative 4, and try another possible rational root. Or remember, this is representing our constant, the negative 4. This negative 4 is the coefficient of our linear term. 1 is the coefficient of our quadratic term. 1 is the coefficient of our cubic term. So we could write x cubed plus x squared minus 4x minus 4. And we could try to factor this instead of going through trial and error. If I'm factoring this, I'm going to split it in half because it has 4 terms, and we need to use factoring by grouping. In the first half, what's my GCF? X squared. When I factor x squared out of both x cubed and x squared, we get x plus 1. In my second half, which is my GCF, negative 4. When I factor out negative 4 from both terms, I get x plus 1. This is good because then I can factor x plus 1 out of both of them. And in my second set of parentheses, I get x squared minus 4. And I need to remember to bring down my original factor that we found, x minus 2. Now we can factor this last factor again because it's a difference of squares. So it will factor to two sets of parentheses, x plus 2, x minus 2. So I have four factors, x minus 2, x plus 1, x plus 2, x minus 2. X minus 2 occurs twice. So I could write it as x minus 2 quantity squared, x plus 1 times x plus 2. So this is our factored polynomial, and our roots, or our zeros, are where our factors equal 0. So x minus 2 equals 0, x plus 1 equals 0, x plus 2 equals 0. Solving for x, we get x is 2, x is negative 1, and x is negative 2. So we have three roots, 2, negative 1, and negative 2. And one of those has multiplicity of 2. Yes, that was all for one problem.